Hello, hello. Yeah, this should be good, right? Okay. Yep.
And you can just turn it off for the next few minutes.
Okay.
All right, welcome to the tree and graph session. We have 3 talks this session. So the first one will be given by Anurag.
Thanks, Yukesh. Good morning, everyone. I'm Anurag, and today I'm going to be talking about ZipG, which is a memory-efficient graph store for interactive queries. Now, this is a joint work with my collaborators Zhongheng and Evan, and my mentors Rachita Garwal and Jan Steiger. Recently, interactive graph queries have become increasingly important, and this is due to the rise of social networks like Facebook, Twitter, and LinkedIn. These interactive queries typically combine queries on graph structure as well as the metadata associated with the nodes and edges in the graph. Moreover, these queries have low latency and high throughput requirements To this end, there have been a number of efforts both in industry as well as in academia to create efforts where they can serve interactive graph queries efficiently. In fact, in just the last 3 years, Facebook has launched its Tau and Dragon graph services, whereas Twitter has open sourced its FlockDB graph service to cater to interactive graph queries. At the same time, open source solutions like Neo4j and Titan have also become increasingly popular. So what are the main challenges in serving graph queries, interactive graph queries? We identified two main challenges. First, the graphs themselves are huge with billions of nodes and trillions of edges, and each of the nodes and edges have several rich attributes. And the systems that store these graphs maintain additional indexes for these attributes to maintain efficiency for the queries. All of these factors contribute to the huge storage requirements for graphs, and in fact, Facebook's reported numbers from 2013 indicate that their storage requirements was almost 1.5 petabytes back in 2013. The second challenge is that the graph queries themselves exhibit little or no locality. And I'm going to illustrate that point with a simple graph query on a social network where we'll try to find all the friends of Alice in Berkeley. Now, the way the modern graph stores execute this query is by first finding all of the friends of Alice by querying the graph structure, and then iterating through the records corresponding to her friends, filtering out those that actually live in Berkeley. Now, the problem is that despite best efforts to co-locate some parts of the graph together, these graph queries touch arbitrary parts of the graph and result in random access patterns that exhibit little or no locality. This becomes problematic when the graph data is spread across main memory as well as secondary storage, and this lack of locality renders caching algorithms ineffective. So the question then becomes, how do you achieve good performance for graph queries when the graph queries themselves exhibit little or no locality? The approach we take is to push as much of the graph data into main memory as possible, and traditionally this has been achieved through compression. However, with traditional block compression schemes like gzip and LZ4, they may be able to push a larger fraction of the data in memory, but they result in poor performance for graph queries because they now have to perform random accesses and decompress a large number of blocks. So how do you achieve good performance for graph queries while achieving a compressed representation of the graph? To this end, there have been a number of specialized graph compression algorithms that exploit the structure of the graph itself to compress the graph as well as execute a certain set of queries on the compressed graph structure. Now, the problem with such approaches is that they're limited to a very small subset of queries on the compressed graph structure alone, whereas modern graph applications actually require queries on both the graph structure as well as the metadata associated with the graph. So the problem then boils down to how do we achieve good compression for the graph queries while preserving performance for these queries, as well as achieving rich functionality that is required by modern graph applications. And this is the main challenge that we're trying to resolve in this work. To this end, I'm going to present ZipG, which is a distributed memory efficient graph store for interactive queries and makes three main contributions. First, it enables a compressed representation of the graph itself, building on a prior work called succinct. Second, using a set of novel data structures and a new graph layout, ZipG enables a wide range of queries to be executed directly and efficiently on a compressed representation of the graph. And finally, ZipG resolves the challenge of supporting queries, supporting updates on compressed graphs by employing a log structured graph representation. So in the next part of this talk, I'm going to focus on the core techniques that ZipG employs. First, ZipG builds on a prior system called succinct, which is a data store that enables a certain set of queries directly on compressed data. Now, this succinct system builds on a data structure called the compressed suffix array, which unfortunately, due to the lack of time, I won't be able to describe. But what I will describe is the interface that succinct exposes. So succinct takes as its input a flat, unstructured file and transforms it into a compressed representation using its compression algorithm. Now, succinct, I'm going to talk about two main operations in succinct that ZipG actually employs and these queries are executed directly on the compressed representation of the data. The first query is a search query, which finds the locations for all the for a particular arbitrary substring in the uncompressed file. So in this example, this search query will find the location of all the green blocks in the uncompressed file. The second operation is the random access operation, which extracts an arbitrary number of bytes from a given offset in the file. So in this example, we're extracting 5 blocks from offset 0 in the flat uncompressed file. Okay. Now, before moving on to how zipg actually exploits these two queries from succinct, I'm going to actually describe zipg's data model and interface. And to do this, I'm going to use a simple toy example with a toy graph example with 3 nodes and 3 directed edges as shown in this figure. Each of the nodes have 2 properties, a name and a location, and each of the edges have 3 properties, an edge type, a timestamp, and a year property. Now 2 of these edge properties are specific to zipg. Edge type, which allows applications to segregate edges incident on a node into different categories, and a timestamp, which forms the sort key for all the edges that are incident on a node. Now zipg exposes a minimal but functionally rich interface that we've actually been able to use to implement a wide range of queries and work from different workloads as shown over here. Now this API is itself composed of queries on the nodes where you might want to get a particular node's specific property, or you might want to filter nodes based on node properties, or you might want to filter the neighbors of a node that have a certain property. At the same time, zipg supports queries on edges where you might want to get all the edges that are incident on a node and lie within a certain time range. You might also want to get any data pertaining to any specific edge in the graph. Finally, zipg also supports modifications to the graph data via append and delete operations on nodes and edges. Now I'm going to briefly describe zipg's graph representation. And at a high level, the way zipg represents its graph is by taking the graph structure and translating it into a couple of flat, unstructured files along with some auxiliary data structures. And these flat, unstructured files are then compressed using succinct. Now this transformation has to be done in a way that ensures graph queries can be executed efficiently on these compressed flat files using succinct's interface. So I'll start with how zipg actually represents the nodes. Now in order to represent the node properties, zipg assigns a unique delimiter to each property in the node of the nodes. In this example, we are assigning a dot delimiter to the name property and a star delimiter to the location property. Now these delimiters will help in searches using succinct, as I'll show in the next slide. But for now, the way the property values themselves are written out for a node is by actually writing out the property values separated by their respective delimiters, as shown over here. zipg also adds a special node record delimiter, which marks the end of all the data corresponding to a particular node. Then zipg writes out the different lengths of each of the properties before writing out the property values themselves. And this is mainly to enable efficient random access to the individual properties of a particular node. zipg also maintains a bidirectional mapping between the node IDs and the data corresponding to these node IDs by maintaining a sorted list of node ID and node file offset pairs. For example, node ID 1 has offset 0 in the node file in this example. Node ID 2 may have offset 0 in the node file, and so on. And all of these entries are actually stored in a sorted list. And finally, all of this node file, which contains the flat unstructured data corresponding to the node properties, is compressed using succinct. Now I'm going to show you a quick example of how zipg actually execute queries on this compressed representation of the node data. So I'm going to use an example where we'll find all the nodes that have their location property set to Ithaca. The first step is to actually identify the delimiter corresponding to location. And then instead of searching for just Ithaca, we're going to search for Ithaca with its corresponding delimiters as shown in this example. And this mainly serves to resolve ambiguities across node properties. Say for instance, if a particular node has both its name as well as location set to Ithaca, this query will only identify location Ithaca and not name Ithaca. Okay, once we have the offsets of the term Ithaca in the node file, we can translate them back into the node IDs by performing binary searches on this sorted array of offsets. This is a simple example of how queries are executed on nodes. Next, I'm going to describe how edges are actually represented in ZipG. Now, in order to transform the edge data into a flat unstructured file, ZipG actually organizes all the edges with the same source node ID and edge type into a single edge record. Now, this edge record is similar to the adjacency list of a node, but instead it is partitioned by the edge type. Now, in order to write out a particular edge record into the edge file, ZipG first writes out the common source node ID and edge type separated by specific delimiters, again as shown over here. It then writes out certain metadata that is specific to that edge record and enables efficient random access into the data corresponding to the edges encoded in that edge record. So in this particular case, we are actually encoding the count of the number of edges encoded in the edge record, as well as the number of bytes that we'll use to encode specific attributes of the edges. This metadata is then followed by the data corresponding to each of the edges, and this edge data is sorted by timestamp, since timestamp forms the sort key for all the edge data in our representation. So we first write out the sorted timestamp values. This is followed by the destination IDs, again sorted by the timestamps. And finally, this is followed by the edge properties themselves, written out in a fashion that is similar to how we wrote out the node properties in the node file. And these again are sorted by timestamps. Now, once we've written out all the edge properties and edge data into the edge file, we finally compress it again using succinct compression algorithm. Now, again, I'm going to show you a quick example of how edge queries may be executed on the compressed representation. And I'm going to use a simple example where we'll try to find all the neighbor IDs corresponding to node ID 1 and edge type friend. So the first step is to search for node ID 1 and edge type friend separated by their specific delimiters as shown in this example. And this is done using succinct search interface. Once we have the offset corresponding to the edge record using this search interface, we can extract the metadata corresponding to the edge record using a random access operation on succinct interface. And then once we have the metadata, we can directly jump to the destination IDs and extract the corresponding destination IDs using another random access queries. And this is how a query may be executed on the edge data. Okay, so far all of my discussion has been confined to how queries may be executed on a static representation of the graph, static compressed representation of the graph. The main challenge, of course, is now graph applications need to perform updates, and this becomes particularly challenging for compressed graphs. So ZipG employs a log structured approach to resolve this challenge, where the bulk of the graph data is actually stored across compressed store servers, which stores the graph in compressed representation, and a set of log store servers actually absorbs all the updates to the graph into append-only logs. And periodically, these append-only logs get compressed into the compressed store. Now, the problem with this approach is that it leads to fragmentation of graph data. And to see why, you can see that a particular, the data corresponding to a particular node gets fragmented across several logs as more and more updates come in for that particular node. And this leads to a problem because queries now have to touch all of the logs in order to aggregate the data for a single node. And this is because they don't know which logs have the relevant data that they're looking for. Now, in order to resolve or mitigate the impact of this fragmentation, ZipG we ran a few studies to determine and quantify the effect of this fragmentation. And by using a large-scale experiment with a relatively large number of updates, we found that while more than 50% of the nodes do get fragmented across more than one shard, the main observation here, the neat observation here, is that most of these nodes, more than 99% of these nodes, have their data fragmented across a very small number of shards. So our approach will actually exploit this second observation. So what we do is essentially assign a specific set of update pointers corresponding to each node in the compressed store, and every time a new update comes in, we append an update pointer corresponding to the new update. And this results in a scheme what we call fanned updates. Now, using this find updates, queries no longer have to touch all the logs to aggregate the data for a single node. Instead, they can simply follow the update pointers and aggregate the relevant data for that particular node. And with this simple optimization, we found that we get significant gains in both query performance as well as updates to the graph. Okay, in the last part of this talk, I'm going to focus on ZipG's evaluation. Now, we've evaluated ZipG against a wide range of systems and for a wide range of data sets and workloads, but unfortunately, due to the lack of time, I'm only going to present a subset of these results. You can find all of the results that we have in our paper. First, I'm going to take a look at the storage footprint for the different systems across different data sets. And on the y-axis here, I'm going to plot the ratio of the system storage footprint to the total input graph size. And the line 1 over here indicates that the input size is equal to the storage footprint of the system. So for the smallest data set, Neo4j and Titan, which are popular open source graph stores, achieve a storage footprint that can be much larger than the input graph itself. And this is because of the overheads in their graph representation, as well as additional attribute indexes that they have to maintain to serve graph queries efficiently. Now, Titan also supports compression using traditional block compression schemes like LZ4, and using this compression, it can achieve a storage footprint that is smaller than the input graph size, but this comes at a cost to performance, as we'll see in the subsequent slide. And finally, ZipG achieves the smallest footprint because of its compressed representation. Now, as we increase the data set size, we observe that the storage footprint trends are almost identical to the smallest data set size, except for the largest data set where Neo4j is unable to load the data even after 48 hours of loading. So the main takeaway here is that ZipG is able to achieve a storage footprint that is much lower than the compared systems, and this is mainly because of its compressed representation of the graph. So next, I'm going to take a look at the performance for Facebook's star workload, which mainly focuses on neighborhood queries that are ordered by timestamps of the edges. We're going to measure the throughput first for the single server scenario, and what we found was for Neo4j and Titan systems, there's a drastic drop in throughput as soon as their graph representation stops fitting in main memory. Now, if you use compression for Titan, the performance degrades even further, and this is because the queries now additionally have to decompress compressed blocks to obtain the results. And finally, ZipG achieves the highest performance across all of these systems, and more importantly, it observes the lowest degradation as the graph size increases, and this is mainly because of its ability to execute queries directly on a compressed representation of the graph without requiring any decompression at all. We've also performed these experiments on a distributed setup, and we found that their trends were almost identical to the single machine setup. Note that we haven't reported numbers for Neo4j because it does not support a distributed implementation. So the main takeaway here is that ZipG observes a much lower performance degradation as we increase the graph data set size because of its ability to execute queries directly on a compressed representation of the graph. Next, I'm going to look at the performance for a much more complex set of queries called regular path queries. And without going into too much detail, at a high level, these regular path queries execute regular expression searches on edge labels of the graph to identify certain graph substructures. Now, we use the GMARC benchmark to generate both the data set as well as the workload for these queries. The workload itself is comprised of 50 different queries with varying nature. Some of these queries were identifying linear and branch substructures in the graph, while a small fraction of the queries were identifying recursive substructures within the graph. Now, I know there are a lot of results here, but the main takeaways here is that for linear and branch queries, ZipG actually achieves up to 35x better performance than Neo4j. Whereas for the recursive queries, ZipG can observe performance that is up to 8 times worse than Neo4j. And this is mainly because ZipG uses a single-threaded transitive closure algorithm to compute these recursive queries. And we believe that we can optimize this transitive closure algorithm to get better performance. But the main takeaway here is that ZipG supports a wide range of complex queries on compressed graphs, with performance that is comparable to or better than Neo4j for a large subset of these queries. With that, I'd like to conclude my talk and say and mention that I've presented ZipG, which is a distributed memory efficient graph store, which supports a wide range of queries efficiently and directly on a compressed representation of the data. ZipG has a functionally rich graph interface and also supports efficient updates using a log structured graph representation. Thank you, and I can take any questions that you may have.
Hi, great talk. I have a question. So you didn't talk much about the distribution aspect. I'm assuming that the node file is sharded by the node ID and the edge file by the edge type and the source.
Yes, that is correct. I mean, the sharding is based on the node itself.
Okay. When are these, sorry.
Hi. One of the well-known techniques for physically representing graph data is vertical partitioning, where you take edge labels and basically partition your database for each edge label and store it in a column store, which by default gives you a lot of compression, right? And on top of that, almost all graph databases rely on dictionary encoding to compress the data further. But I don't see in your experiments comparison against sort of these approaches. So do you have an idea of how well your system does compared to these kind of systems?
That is a fair question, and I will admit that I have not compared the performance for our approach against these columnar-based approaches. And the high-level idea is that ZipG has a partition-agnostic architecture, so that you can employ the same partitioning scheme for ZipG as well. As for the columnar representation, our experiments have shown that we are able to achieve storage footprint that is comparable or better than the compression achieved by columnar representations. And the query execution is better for us when, typically for these queries where I've described it, the queries span the graph structure as well as the metadata associated with these graphs. So the main wins that we get is by being able to combine the compression for both the graph structure as well as the attributes, and combine the queries on both of these efficiently. Thanks.
So have you compared the performance you got with using the alternative storage, like just databases such as Redis, and running Tinkerpop on it and compare? Because if that works, then why do I need to have all this special storage?
That is a fair question, and like I said in the beginning of the talk, a couple of the main problems that we have is because of the storage overheads of these systems, and because of the large storage requirements for both the graph structure as well as the metadata associated with them, along with the indexes that these are, relational databases may maintain. The graph stops fitting in main memory and results in poor performance as soon as an interactive query touches some part of the graph that resides on secondary storage.
Yes.
And that is
so the point is that you could use the Redis cluster, so you could scale it out, so you're not going to hit a limit really. Indexing, I understand, so that's separate. You can use your indexing, that's fine, but the base part of it, you could use these databases. And by the way, these databases are now bringing SSDs into it, so you can cluster up like, even 10 nodes will give you 100 terabyte. I mean, your performance measurement was like 1 terabyte. So for most of the cases, you're not going to hit the limit.
That's fair. I can answer your question offline as well, but like the high-level idea is you can always distribute more. What you're gaining with compression is essentially you can push the same amount of data using fewer servers, or push a larger amount of data across that same large cluster. I can answer your queries more in.
Most of them will fit in one node, by the way. So.
All right, let's thank the speaker again.
Thank you so much.
All right, our second talk will be given by Ken Fei.
Hongxi Zhao from the Chinese University of Hong Kong. Our study is focused on graph processing in relational database system revisit. My presentation is divided to, my presentation is divided into this part. Firstly, I will introduce our motivation in graph analytics in RDB, and I will review the related works. And then I will introduce the limitation of recursive query in two aspects, since most of the graph analytics algorithms are recursive algorithms. And I will propose our solution with 4 new relational algebra operations added, and followed by our enhanced recursive query and its implementation. Finally, I'll introduce our performance study with a summary of our key points. Since graph is a popular data model for interrelated data such as social network, biological network, and knowledge graph, a lot of graph analytic algorithms have been proposed for wide applications. And there are many specialized graph processing systems which have been proposed recently. But there are very few exploration about traditional relational database, especially graph processing on SQL level. The question we need to reconsider is why we cannot use SQL and what SQL can do for us. The differences between these two kinds of systems motivate us to explore this topic. And there are another reasons and the scenarios where we would like to turn to relational database system or graph analytics on SQL level. For example, a graph may be extracted and RDB initially, and it is probably associated with relational data. And the users sometimes need to query and manage graph by familiar language, and it's very labor consuming to migrate the data and manipulate the specialized graph processing system. Here I will review the related works briefly. Firstly, there are many graph query languages, and many of them are also SQL-like query languages. But our research now focuses on just use the elements in the SQL level to design a general framework to express graph processing, graph analytics algorithm as more as possible. And also a few graph queries as designed and optimized in the relational database environment. However, these queries is always used for specialized specific graph applications. And recently, the data load-based system has been proposed for graph processing recently. However, data load is not good at for data management. Since most of graph processing algorithms are recursive, here we trace back from the SQL recursive query. The SQL recursive query here we also call recursive common table expression. It defines the recursive relation by the in the initialization step, and it queries the recursive relation R iteratively in the recursive step. And here is an example of linear transitive closure. In the initialization step, the recursive relation TC is defined by projection of the two columns F and E from the H table E. And in the recursive step, the TC will join E, and the delta part of the result is merged into the result TC by the set operation union all. The recursion ends when there's no tuple generated anymore. And the SIGMOD recursion involves two key concepts called nonlinear and mutual recursion. The nonlinear recursion results twice or more referring to the same recursive item. It converts fast but hard to implement, while the mutual recursion as recursive item indirectly refers to itself. It's worth mentioning that, unfortunately, SIGMOD does allow nonlinear recursion, and the non-existing database system supports neither these two kinds of recursion. And SIGMOD also have restriction on the monotonicity of in the recursive part. The monotonic query is when new tuples adding into the database, the result relation does not lose any tuple. Here, the 5 basic relational algebra and the theta join are monotonic query, while query involves aggregation and value updating are non-monotonic query. In the computational theory, programs with no monotonic query in recursion is called stratified program. According to the famous Katie theorem, monotonic operator T has a least fixed point, so that SIGMOD and existing relational database only support stratified recursion. And last steps into the specific functionalities of different relational database systems. Here we investigate 3 mainstreaming RDB. We can see this table. Here only DB2 support multiple query in recursive step, and only Postgres support set operation other than union all to connect the initial and the recursive query. And there are many restrictions of the monotonicity in the recursive part of these three systems. All of them disallow nidation, aggregate function, and group by in the recursive part. However, they support partition by and analytical function. And fortunately, DB2 even disallow general functions. By the way, Oracle also have its own mechanics to do looping control. So far, we have found SIGMOD has its power to support some recursive graph computation, such as the linear transitive closure. However, it also has many limitations in recursive part, such as the nonlinear and the non-monotonicity. So this motivates us to find a solution in which 2 interrelated issues should be considered. One is how to support a large graph algorithm with a set of operation as more as possible, and the other is how to draw a line for the semantic of the query. Now here we move to the first answer. In our studies, we model graph as weighted directed graph. It's stored in vertex and edge table in the database system, considering the matrix representation of the graph. A semi-ring calculus of matrix corresponds to the procedure of vertex send and merge message on the graph. Therefore, we have the operations called MV and MM join, which are defined by the algebra structure semi-ring there are two steps. Take the MV join, for example. The first step is join A and C by the join condition. The second step is group by and aggregation. Given the proper operation of addition and multiplication of semi-ring, the MV join can support a range of typical graph algorithm. And MM join is regarded as a high-dimensional version of MV join, where each vertex holds and compute a vector instead of a scalar. And here we also use another two operations, which the one is called anti-join. It serves as a special selection to filter nodes or edges, which is unnecessary in the following computation. It defines as the relation R, which cannot be semi-joined with the relation S. And the other operator is union by update. It updates the value of R by the value of S if the given column R and S have same value. The union by update is used to address value updating in the iterative computation. In addition, we also need a control structure. Here we use the algebra plus wheel semantic. R is a real sign by evaluating the relation algebra expression. The looping will terminate it until R becomes stable. There are two semantics of the assignment here. One is a cumulative assignment, which corresponds to the union all. The other is destructive assignment, corresponding to the union by update. Here with these four operations, this table shows some representative graph algorithm can be supported other than linear transit closure. For example, the MV join plus union by update can support page rank, random work with start, weakly connected component, hints, etc. With the four new operations, we still need to answer the second question, how to analyze the semantic of the query. As these four new operations are all non-monotonic, they lead the query beyond stratified negation. It's quite difficult to answer this question directly. So we put this relational algebra expression into the text of data log so that we can deal with this question by the add of data log. Fortunately, all of the operations we use have an equivalent data log rule. The enhanced recursive query corresponds to a data log query, such as the page rank query at the bottom of this slide. In the theory of data log non-monotonic reasoning, there is a kind of program called XY program. And the XY program whose bi-state version is stratified is called XY stratified program. In 1995, Carroll proved that the XY stratified program is locally stratified so that it has a unique state model which equals to the iterative fixed point. We further proved that our enhanced query with the four new operations added is XY stratified so that it inherits its semantics. This feature can be checked at compiling time. Okay, so come back to our enhanced recursive query. Here we use the example of PageRank to demonstrate the differences between original recursive query and our enhanced recursive query. Please note the original with query of PageRank can only be supported in Postgre. The differences lies in mainly 3 points. It uses union all, so it consumes all the intermediate result. Where we use the union update for value updating, it requires distinct and the analytical function. However, we use the group by, and it's also an extra column L for recursive depth, and here we use the label max recursion. And for each query queue in our enhanced query, we support compute by clause. This clause allows specifying how queue is computed by a sequence of queries. Please note recursion as disallowed in the compute by clause. It means the dependency graph of this queue must be a DAG. Here's the general form of our enhanced recursive query. It consists of several select statements connected by union or one recursive part connected by union by update. When the query issue, we generate the corresponding dependency graph to analyze the dependency relationship of the query, and then stored procedure is generated automatically, and this which can be executed by the underlying database system. And here I will report our performance status. Here we test our enhanced recursive query on 3 database systems for 9 real-world graphs, and we implement 10 algorithms, which covers all of the 4 operations we proposed. And this figure shows the overall performance of the 9 algorithms. We found that the relational database system have the capability to do graph processing in reasonable time. There are 2 factors to influence the query performance. The one is the number of the iteration, the depth of iteration, and the other is the number of type of the recursion in each iteration. And we test the effectiveness of indexing for the MV and MM join over the Postgres system. We find building B+ tree will change the query plane from full table scanning to index scanning. And then we compare the performance of Oracle to 3 specialized graph processing systems. Here they are Datalog, Giraffe, and Power Graph. The Socialite and the Power Graph is memory-based system, and Giraffe is built on the Hadoop framework. We find for PageRank, the Oracle can beat Giraffe on most data sets, but it cannot beat for connected component and shortest distance. The reason is for the specialized graph processing system for Giraffe, they have very different patterns of message sending and merging. And here finally we compare the original with and our enhanced recursive query for PageRank on Postgres and transit closure. Our enhanced recursive query works well for outperform for PageRank on Postgres, and it can achieve a very similar performance for the transit closure. So here's all of our performance study. So finally, I will summarize our key points and main idea. Through our investigation, we find CQ99 can only support linear transit closure since it can only support stratified program. However, our enhanced recursive query, since adding the 4 new relational algebra, we can support a large range of representative graph analytic algorithm, and we prove that it lies in the XY stratified program. In the experimental study, we show that the traditional database system have the capability to do graph computation in reasonable time. So that's all of my presentation. Looking forward for your question. Thank you.
So, just a high-level question. Did you try like distributed? Like, so most of your data sets seem very small to me, and I wonder if your experiments were done on like a single node or like a parallel database. Were your experiments done on like a single node database or like a parallel database?
You mean the single machine?
Yeah. So did you do them over like
Yeah.
one MySQL instance or like a sharded MySQL instance or something like that?
Yes, in the previous research stage, we only test this for single machine,
But most big graphs, most meaningful graphs cannot fit on a single machine. So what's the point?
you mean most? I think that's our future study area.
Thank you.
Our future study is how to support this query in the parallel environment.
Thank you.
So there was a comparison that you done with Girov, right? There, don't you? And another thing I wanted to ask about related work. There's other experiments that are similar to it, like Vertexica and a SQL graph from IBM. How is it related with it? That I saw that you didn't mention.
Through this work, we just want to show how to use the SQL to express the graph analytics algorithm. I think previous study didn't have a extensive study of how to express this operations. Yes, I think they have proposed similar operations, but they haven't explained how to use this in recursion. We just want to show to use this operations in the recursion. Yeah.
I see. Thank you.
All right, let's thank the speaker again.
No? The order gets switched?
Yeah, this one.
Okay, that makes sense.
Okay, our last talk will be given by Li Jing.
Good morning, everyone. So welcome to my talk. My talk is about computing independent set of large graphs. So this is a joint work with Wei and Wenjie. So here's the outline. First, I will give the introduction. So an independent set is a subset of vertices such that there's no edge between any two vertices in the subset. So a maximum independent set is an independent set with the largest size among all such independent sets. So for example, for this graph, these four vertices is our independent set because there's no edge between any two of them. However, it is not a maximum one. So this is a maximum one with 5 vertices. So this problem has application in building an index for shortest path queries and also in refining the result for subgraph for matching to large graphs, and also can be used for social network coverage, which is to compute the vertex cover. Actually, the vertex cover and the independent set are just similar to each other. Actually, the same. The result just complement each other. But this problem is a very hard problem. Firstly, it is MB hard to compute. And also it is hard to approximate, which means that given an arbitrary constant epsilon, we can, it is MB hard to approximate the result within a factor of n to the power of 1 minus epsilon. So which means that we cannot hope to find the approximation result with approximation ratio larger, better than n for an arbitrary large graph. So the existing works are mainly categorized into 3 categories. The first is the exact algorithm. So this is a study in the graph theory. And the second is the approximation algorithms. And the third is the heuristic algorithms. So the exact algorithm is based on the branch and the reduced paradigm. So actually, the previous work proved the time complexity for this paradigm, which is obvious is exponential. Recently, I think it's last year, several authors showed that actually this branch and reduced paradigm can work very well for many small and medium-sized graphs. This is because actually these graphs are easy to process. But however, this method still cannot efficiently process large graphs. And the existing approximation algorithms, the approximation ratio largely depends on n or the maximum degree. So the maximum degree in the worst case can also be n. So this, which means this is followed from the previous hardness or result of the approximation. So this approximation ratio actually are not practically useful. So most practical solutions are heuristic algorithms. This also 2 lines of research. The first is the linear time algorithm. So this is very simple. First is the grid algorithm, and also the second is the dynamic update. So the general idea is the same. Each time we pick the vertex with the smallest degree, and then we add this vertex into an independent set, and we remove all its neighbors from the graph. So the difference between these 2 approaches is that the grid algorithm, we just sort all the vertices by their degree in the initial stage, and then we scan this sequence in this order. But in the dynamic update, each time after we remove a vertex from the graph, we need to update the degree of a vertex. So both algorithms can be done in linear time. So the second line of research is iterative randomized search. So actually, most of them are based on the first. The following 2 are based on the first algorithm, based on the local search algorithm ARW. So the reduced MIS and online MIS are just 2 variants of the ARW. So they use evolutionary techniques and also use some simple reduction rules. So the first linear time algorithm, it's very efficient because it has a time complexity guarantee, which is linear. But it can only find a small independent set in practice. The second approach can find very large independent set. If we give enough time, maybe for example 1 week or maybe 1 month, then you can find a large solution for large graphs. But this takes a very long time. So the main goal of our work is to find a large independent set in a time-efficient and also space-effective manner. So in order to do so, we propose a reducing and repeating framework. So the framework is based on 3 main observations for real-world graphs. So this means that our solution may not produce the good result for the worst-case graph. So the first observation is that many real-world networks are usually power law graphs, which means that there are a lot of vertices with a small degree and also a few vertices with a very high degree. And the second observation is the reduction rule actually can be very effective for handling the low degree vertices. Actually, this observation has also been observed in some of the existing works. So there are two main reduction rules. The first one is the degree 1 reduction. So the idea is very simple. So if U is a vertex of degree 1, so obviously there is a maximum independent set that contains U. This is because if there's a maximum independent set does not contain U but contain V, then we can swap these two and also got a maximum independent set. So the second reduction rule is to handle vertices of degree 2. So there are two cases based on whether the two neighbors of the U are connected or not. So if the two neighbors of U are connected to each other, then we can safely remove both neighbors V and W from the graph without affecting the independence number of a graph. So here the independence number of a graph is the size of the maximum independent set. So here we only care about the independence number. So actually for graphs, the number of different maximum independent set can be a lot. So we just need to find one. The third observation is that usually high degree vertices are less likely to be in a maximum independent set. So the intuition is that if we pick a high degree vertex into the independent set, then we need to remove all its neighbors from the graph. Actually, this neighbor set is very large. Also, if we remove a high degree vertex from the graph, this operation can sparsify the graph, which usually we can partition the graph into disconnected parts. So we based on these three observations, we propose this framework. So in this framework, we define inexact reduction rule. So in the previous slide, I showed the degree 1 reduction and the degree 2 reduction. These are the exact reduction rules. So if we apply this reduction rule, we will not, we still guarantee the maximum independent set. But here in the inexact reduction rule, if we apply this one, we may not obtain the maximum independent set. So in this framework, it mainly contains of two phases. In the first phase, we will apply the exact reduction rule. As long as we can apply one exact reduction rule, then we apply the reduction rule. So if the exact reduction rule cannot be applied on the current graph anymore, then we apply the inexact reduction rule, which means we try to remove the vertex with the maximum degree. So we iteratively apply these two phases until the graph contains no edges, which means it's empty. After this, we do a post-processing. So in the phase 2, we actually remove several vertices. So which means that after these two phases, the independent set may not be a maximum one. So we can add some new vertices into the independent set, which have been removed by the inexact reduction rule. So we do this as a post-processing step. So here is a general overview of our approach. So we compute this in a time-efficient and space-effective manner. So here the time-efficient, which means that usually we want this to be at least to be sub-quadratic to a number of maybe to a number of vertices, because we are dealing with large graphs. So usually the linear time will be better. The linear means linear to the number of edges. So here the space in a space-effective manner. So space is we want it to be 2 times m plus big O n. So here we distinguish two constants for m and n. For m, we specify the constant to be 2, and for the n, we just be any some constant. This is because in real world, especially large graphs, this memory space to store a graph actually is dominated by the edges. So here we use a graph representation. We call it as adjacency array or a compressed bus row in the matrix literature. So the graph can be stored in by 2m plus n integers. So which means that actually in our algorithm with very little overhead in addition to the graph storage. So by this graph storage and by this algorithm, actually a graph with 1 billion edges usually can be stored by a little bit more than 8 GB of memory. So actually in our experiments, we conduct other experiment on a machine with 16 gigabytes, and the largest graph contains 1 billion edges. So here, within this framework, we propose 4 approaches, which will be illustrated in the following slides. So the first one is our baseline algorithm. We just apply the very simple degree 1 reduction and also the inexact reduction. So I will show you the algorithm works by example. So here in this example graph, there's one vertex with degree 1, which is V1. So by the degree 1 reduction, we remove its neighbor, which is V2 from the graph. Now, in the remaining graph, we cannot apply the degree 1 reduction because there's no vertex with degree 1. So we apply the inexact reduction. We remove V6 from the graph. And now, actually, after we remove V6, we can now recursively apply the degree 1 reduction because both vertex V3 and V4 are of degree 1. So we remove V5 and we got an independent set, 3. So for this simple algorithm, the time complexity is linear to the number of edges, is OM. And the space is 2M plus O, big ON. And the second baseline algorithm is we call it BD2, so we apply both the degree 1 reduction and the degree 2 reductions, and also the inexact reduction. So in both the BD1 and BD2, we apply the existing reduction rule for handling degree 1 and degree 2 vertices. So for BD2, actually the first step is the same. We remove V3 from the graph. Now in the remaining graph, we actually have V3 and V4 of degree 2. So we apply the degree 2 reduction. We can remove V5 and V6 from the graph without affecting the independence number of the graph. So we obtain the independent set consisting of 3 vertices. So we show that this algorithm, the time complexity is big O n times m. So this is very loose analysis of the algorithm because we are not able to get a very tight analysis. But we also prove that this is lower bounded by m plus n log n, so which means it is not linear to the number of edges. Another drawback of this approach is the space. Because in this space, actually, we need a contraction operation. We need to contract several vertices into a single supervertex. So in this way, we need to modify the graph structure, which means that we need another graph representation. So this takes larger space, which is 6 times m plus big O n. So actually, degree 2 reduction actually is very effective, but it is not efficient. So we propose a new reduction rule to handle the degree 2 vertices. We call it a degree 2 path reduction. So consider a graph with a minimum degree 2, then we choose a maximum degree 2 path. So a degree 2 path is a path in which every vertex has a degree exactly 2 in the range graph. So let P be this maximum degree 2 path, and V and W are the 2 neighboring vertices to the path P. So V is adjacent to V1 and the W is adjacent to VL. So then we will handle this degree 2 path individual for each different case, how V and W are connected or be the same. So in the first case, this V and W are the same. So which means that we actually have an induced cycle in this graph. First, I think I need to mention that actually this degree 2 path can be obtained in linear time to the size of the degree 2 path. So we can actually find this degree 2 path efficiently. So the first case means that this graph contains a cycle, induced cycle. So we can remove this vertex V, which is not of degree 2. So we will not this will not affect the independence number of the graph. In the second case, so in the following cases, V are not equal to W. So in the second case, V is connected to W, and also the path is of the length of the path is odd. Then we can remove both V and W from the graph without affecting the independence number. So after we remove this V and W, then for the remaining vertices in the degree 2 path, actually we can we can obtain the best optimal result by applying the degree 1 reduction. So the third case is similar to the second case, but V and W are not connected to each other. So here we need to add an edge between V1 and W. Actually here V1 and W and V and VL are symmetric to each other. Actually we can also add an edge between V and VL. So after we add an edge between V1 and W, then we can remove the remaining P-1 vertices from the graph. Then the optimal result actually can be obtained from the remaining graph, and then plus half of the vertices in the path. So which vertices from the path will be included into the independent set actually will be determined by V1 and W. So from V1 and W, we add at most one vertex to the independent set. So after we choose one vertex to the independent set, then the remaining vertices from V2 to VL can be decided uniquely. So the fourth case is also similar, but here the length is even, and for this case we just remove this path from the graph. And for the fifth case, it's similar to the fourth case, but there's no edge between V and W. Then we add an edge between V and W, and then apply this fourth case. So here is an example of running example of this algorithm. So first we obtain this degree 2 path, which is V1, V2, V3. So we remove V4 from the graph. Now we obtain the degree 2 path, which is V5 and V6. So we will temporarily remove these two vertices from the graph. We also need to add an edge between V7 and V10. So after we obtain the best the independent set, which is V10 from the four vertex clique, then we know that V5 cannot be added to in the independent set, so we add V6 to the independent set. So we also prove that the space complexity is 2m plus On, and the time complexity is big Om. So previous is a linear time algorithm. We also designed a near-linear time algorithm. So this is based on a concept of domination. So a vertex V dominates its neighbor U if all the neighbors of V are connected to U. So in this way, it is always safe to remove U and maybe add V to the independent set. So we prove in this paper that a vertex V dominates its neighbor U if and only if the number of triangles containing V and U equal to the degree of V minus 1. So in this way, we will maintain a set of candidate dominated vertices, and we also maintain the number of triangles containing each edge. So in this way, we can identify the candidate of dominated vertices in constant time for each vertex. So the time complexity is big Om times the maximum degree, and the space complexity in the worst case is 4m times plus big On. This is because we need to maintain the triangle for each edge. So however, in practice, actually this can also be done in 2m plus big On. This is because actually we can first apply the degree 1 reduction and the dominance reduction, one pass dominance reduction, which usually will reduce the graph size by at least 2. So then we can rearrange the graph and use the another half to store the number of triangles. This way we will not increase the memory space. So we also extend our algorithm for iteratively enlarging the results, and also computing an upper bound for the maximum independent set. So here are some experimental results. We conduct a lot of experiments on many graphs. So the largest graph contains 1 billion edges. So we use only one a normal PC with 16 gigabyte memory. So here are the accuracy results. So here, actually in the second column, you can see that we show the independence number. So this number is computed by an algorithm which can compute the exact solution, but may take a very long time. So here, this data set is only a subset of previous data set. This because here we only show the result for the graph that the exact solution can compute in 5 hours. So for other graphs, the exact solution cannot finish in 5 hours. So here, the algorithm greedy and the DU is dynamic update, and the semi actually the semi-external algorithm based on the greedy. So you can see that actually our algorithm can almost obtain the maximum independence set for most of the graphs. And for other graphs, we do not obtain the maximum independent set, but the accuracy is still over 99%. So here are some the process the processing time. So in the first figure is the processing time compared to the existing linear time algorithm. You can see that the BD1 is actually with similar running time with the existing algorithms. And in the second figure, you can see that actually our linear time and the near linear has a similar running time with the BD1. So because linear time actually has a linear time running time guarantee, but for the near linear, although its time complexity it depends on the maximum degree. Actually, after first several reduction rules, the maximum degree can be reduced significantly. So it also may run in linear time in practice. But for BD2, the running time is a little bit higher than the linear time. And the VC solver is the exact solution, so which may take a very long time for some graphs, even not so large. So here is memory usage. So in the first figure, also we compare with existing solutions, which are very simple ones. So we take linear memory space. So BD1 is similar to the existing ones. And the second figure, you can see that also linear time and the near linear time has a similar space usage as BD1, but BD2 takes larger space. Also, the VC solver takes a much larger space. So here is the result of applying our algorithm to get an initial result, and then we run the ARW to iteratively improve the result. So here, this x-axis is the time. So y-axis is the number of is the independent set size. So each time after we got a larger independent set, so we call the time and the independent set size. So we put a point in this figure. So you can see that the ARW NL is the ARW initialized by our near linear time algorithm, and the ARW LT is initialized by the linear time algorithm. So both ARW LT and ARW NL actually find very close to the maximum to the optimal one found in 3 hours. Yeah. So here's the conclusion. We produced a framework and also several efficient techniques. Okay. Thank you.
Thank the speaker.
Thank you for your talk, and I have one question. So is it possible to estimate the gap to the maximum independent set size without running an exact method?
Sorry?
Is it possible to estimate the gap to the maximum independent set size without running an exact method, without knowing the exact value?
I think it's not easy option. So because of the approximation hardness of approximation solution. Yeah, because of this approximation hardness, so it is impossible.
I mean that I think that it might be possible to obtain how the obtained solution is worse compared to the optimal solution. For example, the gap is some kind of not the exact gap, but some upper bound of the gap, estimating the upper bound of the gap.
So yes, no, I understand.
Sorry. I see. Thank you.
Yeah. So actually for this result, you can see that actually we mark some of the results in different font, bold, because actually for this result we can make sure that it is maximum, maximum one. But otherwise we cannot make sure any of the approximation ratio.
I have a question about the accuracy here. So is that based on the number of independent set?
Yes.
do you have accuracy based on the number of nodes? Like if you have a missing independent set here, how many nodes are there in that missing set?
You mean how many nodes in which point?
Like if it's not accurate, for example, the live journal case, how many nodes are missing in your final, like are not included in your
this is actually the definition of the gap. So because our solution is an independent set, it's just not the maximum one. So we just may miss some one. So this is the gap.
Yeah, I know. I mean, the gap, you are measuring the gap using the number of sets. But I mean, do you have a number like how many nodes are there in the missing set?
Yeah, the independence number minus the gap is the independent set we found.
Yeah, I know, but it's a number of set, right?
Number of vertices.
A number of okay.
Yeah, this is one independent set. So we do not have different independent sets.
Got it. Thank you.
All right, so let's thank the speaker again. So that concludes the session. Thank you very much.
这个是我来之前感冒了。
错，对啊，要关一下。